All right, good morning everyone, and thank you for coming to this Autodesk Support webinar series. Today we'll be building our simulation composites IQ. And in the past few months we've had a lot of work being done to the simulation composite analysis product. We've got a lot of new features available, and we have the product manager for that product. And he's going to speak with us today and go over some of these features. And I'd like to introduce him now. His name's Doug Kennick.
Cool. Thanks, Dean. I appreciate it. Hey, everyone. Doug Kennick here. I'm the product manager for Autodesk Simulation Composite Analysis. And for those of you that don't know, Autodesk Simulation Composite Analysis is a composites simulation tool that bolts onto your traditional finite element package. So you can run it with Atticus, ANSYS, MSC Nastran. As an add-on, it works as a user-defined material subroutine, so it works with the FEA analysis to specify material properties during a nonlinear analysis. And it's very powerful in the fact that it can predict fiber or matrix failure, or a combination of both, as well as update material properties during a nonlinear analysis to account for matrix cracking or fiber breakage. So you can see the ultimate structural life or ultimate structural load of your composite part, as well as determine the failure mode. So you can start making design decisions based on failure load and mode. Today we're going to talk about what's new in Autodesk Simulation Composite Analysis 2015.1. 2015.1 was released in November and has been commercially available for the past few months. And there was one significant enhancement that we made at 2015.1 that I'll cover in a lot of detail today, and that is the interface with Autodesk Moldflow. So here's a list of what's new in 2015.1. I'll make sure to hit each of these independently, but the first two are very related. So we added a new utility in Autodesk Simulation Composite Analysis called Advanced Material Exchange. For those of you who are familiar with Project Sundance, this is Project Sundance in its commercialized form. Advanced Material Exchange is a new front-end tool that comes with Autodesk Simulation Composite Analysis, and it allows you to map data from a Moldflow simulation to an Atticus structural input file. On the back end, or in the solver, the portion that works with the finite element analysis as a user-defined material, we added support for chop fiber microstructures. And this is the portion that allows us to use that map data from Moldflow to Atticus using the Advanced Material Exchange in a nonlinear analysis. So we can use fiber orientations, residual stresses and strains, and we can actually use an elastic plastic material law and predict matrix rupture or failure. For continuous fiber composites, we added a new API so users can specify their own damage initiation and evolution routines. And we also added some speed enhancements. Between the 2014 and 2015 versions of this product, we noticed a significant speed hit or efficiency hit, and we're all about our efficiency over here, so we decided to upgrade and update our code to get rid of those problems, so now we have some speed enhancements. So let's talk about the Advanced Material Exchange. Again, this is the new front-end utility that comes installed with Autodesk Simulation Composite Analysis for free. What it does is it maps material properties, fiber orientations, and residual stresses and strains from a Moldflow simulation to an Atticus structural simulation. So you can see on the screen on the bottom right in the picture, we have a Moldflow simulation on the right-hand side of the screen and a structural simulation on the left-hand side of the screen. Typically, with chop fiber microstructures, it's very difficult to specify what the material orientations are because it is a function of the manufacturing process. So in Moldflow, a lot of the times what we're doing is changing the gate locations for injection molding, we're changing part thicknesses, and we're trying to optimize the design either to minimize warpage or to get the fiber orientation in a certain direction. We want to take advantage of that for the structural part. So most often what happens in Atticus is that we assume an isotropic material and a linear elastic response, and we use that material definition to design for the structural component or for stiffness or strength. When in fact, what we really should be doing is taking into account those material orientations and the residual stresses and strains, and we should be using that in the Atticus structural simulation And then we can design for true stiffness of the part. We can design away from failure modes, and we can also determine if we're going to have any yielding or matrix rupture. So the whole goal of advanced material exchange is to take the data from mold flow to a structural analysis. Here's a list of the supported mappings. Right now we support solid to solid, which means that you can run a 3D mold flow simulation and you can transfer the fiber orientations, material properties, and residual stresses and strains to the structural analysis. The structural analysis supports a host of different solid elements. We'll talk about it in a second. We also support midplane to shell, so you can run a midplane analysis in mold flow, and then you can transfer those results over to the structural analysis with shell elements. And I'm going to pause this for a second to show you can actually view results in different layers. There's a slider on the top of that UI that allows you to step through the different layers of the shell so you can determine what the fiber orientations are doing through the thickness. Here's a list of the supported Atticus elements. Currently we support C3D4 and C3D10 tetrahedral elements, that would be for solid to solid mappings, as well as C3D8, which is an 8-node hexahedral, and a reduced integration hexahedral for solid-to-solid mapping. On the shell side of this, we support an S3, which is a 3-node shell, an S4, which is a 4-node shell, fully integrated, and an S4R, which is a 4-node fully or reduced integration shell. So those are supported element types in Atticus for both solid and shell elements. One big thing we noticed when we had Project Sundance was that we were missing a few key functionalities. The first of that is model alignment tools. When we released Project Sundance, we were assuming that the two parts were oriented in the same global position or spot. And oftentimes that's not the case. What we typically see is that the mold flow part is oriented in tool space and the structural part is oriented in the analysis space for the total assembly. So I like a good example of this is car space. What we see often is that, let's say the spring is on a car, it's oriented completely different than what we would orient it for the for the manufacturing simulation using mold flow. So there needs to be a way to align the two models correctly. So what we've done is we've added a few utilities to do this. One is automatic alignment. If the two geometries are similar in shape and size, what we will do is automatically align the two models for you, and all you need to do is click a button. And that's what we're showing on the screen right now. We also have an interactive alignment. This allows us to interactively align the two components. So in the case where the two parts are not the same, maybe we have more geometry on one or another, or maybe they are not the same size, what we can do is actually rotate and translate the structural side of this so we can position it on top of the mold flow simulation. And now they share the same coordinate system, the same global position, and we can map the data efficiently. Here are the various requirements for advanced material exchange. We require that you have mold flow insight premium so that we can acquire all the necessary data from the mold flow simulation. Remember, right now we're only supporting chop fiber microstructures. We also require that you have Atticus 612 through 614, and this can be both implicit and explicit. Our code will also run on Linux clusters. When you want to run a nonlinear analysis using advanced material exchange, you need inputs besides those linear inputs that come from mold flow. So we also require that you input two stress strain curves that are nonlinear to failure. One is aligned with the flow. So if this is our plaque and this is the gate, we have flow coming in. Aligned with the flow would mean that the plaque would be cut out of these test specimens would be cut out of the plaque, aligned with the flow. So we would need one stress strain curve aligned with the flow. We would also need one stress strain curve perpendicular to the flow. That allows us to fully characterize the composite material for the structural analysis. If you have the data, we also like to have 45 degrees to flow, as this just allows us to calibrate our material models a little bit more accurately. Here are some limitations and strengths of advanced material exchange. Some limitations: that is Atticus only right now, and we can only map data for a single part, so we can't handle assemblies of multiple plastic parts. What we can do, though, is we can map data from mold flow to one part of an assembly in Atticus, or one section from a part. So you can have an assembly of multiple parts, and we can map the data for one of those parts. We only support fiber-filled materials, chopped fiber materials right now, and we can't support compression molding. The major strengths of advanced material exchange, however, are that it ignores runners, molds, and cooling lines. So anytime that you bring over a simulation from mold flow, a lot of times there will be runners, molds, and cooling lines that aren't applicable to the structural analysis. So anytime that you bring the mold flow simulation into advanced material exchange, we will automatically ignore those features. It also imports short shots. So in the case where there is not enough mold flow geometry and more structural geometry, we will still map that data. On the other side of that, we can pretty much map any geometry to any geometry, which basically says that if your structural component has less geometry than your mold flow component, we can map all the data over and fill the structural component. But we can also map data when your mold flow component has less geometry than your structural component, which means that some of the structural component won't have mapped data. We would just require you to specify what the material properties are for those portions we do not map. So that's the advanced material exchange. Again, that is the new front end that allows you to map data from mold flow to an Atticus structural simulation. To complement that, what we've done is we've added chopped fiber microstructures, these micromechanics models, failure models, plasticity models, to the solver end of our code. So this is the end of the code that actually works with Atticus during the structural simulation. Once you map all the data over using advanced material exchange, it creates a file. And that file is called a .sif, or a short fiber interface file. The solver of Autodesk Simulation Composite Analysis is the only solver that can read that data. So it will read all the data, including the fiber orientations and the residual stresses and strains, and we'll map that over to the integration points and elements of the structural analysis. So now we have a point-by-point description of the material and the fiber orientations across the entire structure. Once we have that data, we can actually perform nonlinear finite element simulations. And we've included an elastic plastic response of the matrix constituent, so we can include plasticity, as well as failure predictions of the matrix constituent. So at this time, we're assuming that all of the nonlinear behavior of the chopped fiber composite is embedded in the matrix constituent. We actually work at the fiber and matrix level. So anytime the matrix exhibits any plasticity or failure, we'll actually build the response to the composite back up and feed it back to the structural finite element code. So here we're showing, on the screen, we're showing a mold flow simulation. It's brought in advanced material exchange. We've mapped the data from mold flow analysis to the structural analysis. And we bring it into Atticus, and we're showing the deflection of this part. So I'm going to go back one. Let me get through really quick. So you can see we're looking at the von Mises stress, and what we've done is we basically fixed this thing up by the bolt holes, and then we're putting a pressure on it down here, and we can see a large stress concentration that's occurring around this flat region where it's fixed. And what's actually happening is we're getting a large amount of plasticity here in the matrix constituent due to high bending loads or high tensile loads that we're seeing right there. Okay, so that is what's new in the advanced material exchange and the new chopped fiber microstructure support in our solver, which supports mapping data from mold flow to the structural simulation. On the continuous fiber side, we've also included an API for damage initiation. What that allows customers to do is to define their own failure criteria. So Autodesk Simulation Composite Analysis offers a host of failure criteria that you can use in an analysis, including max stress, max strain, Hasheen, Sci-Hill, Sci-Woo. But a lot of times, users want to be able to define their own failure criteria. And more than that, they want to work at the fiber and the matrix level. So they want to define failure in the fibers or the matrix independently. So we've allowed users to access constituent information, which means that they have access to fiber and matrix stress and strain fields for both woven composites and continuous fiber unidirectional composites. You also have access to our own MCT failure criteria. So once you have acquired the information at the fiber and matrix level, you can ask what our failure criteria would say the failure mode is, as well as what the resulting ratio is to failure. So you can start making decisions prior to any failure in case you wanted to include any material nonlinearity. We also give you access to our microstructures, which means that you can run the micromechanics codes in the background, or you can determine if it's a woven material or a unidirectional material. We've also included an API for damage propagation. So damage propagation, what happens after failure, is typically what controls nonlinear progressive failure analyses. And there are a host of different methods to degrade material properties and evolve damage in a finite element analysis. And these need to be based on some sort of physics observation. So we created an API for users to define their own damage evolution, what happens after failure. And this is for only for continuous fiber unidirectional composites. Well, the nice thing about it is that it's IDSM controlled. IDSM is short for Intelligent Discrete Softening Method. What that means is we have a proprietary technology that works with our solver that helps solve convergence problems, and it's called IDSM. Typically, when users run progressive failure analyses of composite materials, they almost instantaneously run into convergence problems because composite materials are have very discontinuous failure modes where their stiffness will be very high at one point, and once they fail, the stiffness will almost instantaneously drop to a very low value. And when that happens, finite element codes have a very difficult time converging on a solution. So we have technology that helps finite element codes push past that so they can stay efficient. So in the API for damage propagation, we've allowed users to access constituent information, which means that you have fiber and matrix stress and strain fields, as well as microstructure information. So you know fiber volume fractions, you know that it's continuous unidirectional composite material. We've also provided access to our micromechanics routines. And this is fairly powerful because what you can do is you can degrade or make decisions at the fiber and matrix level, evolve damage, and then you can build back up the composite response and feed that back to the finite element analysis. And it's all wrapped under our own convergence technology. That's what I have. How's that, Dean? 20 minutes? Do you have any questions?
Thanks a lot, Doug. Yeah, feel free, everyone who's attending, to type your questions into the box below, and we'll read them out loud.
All right, so I have one here. I don't know if you want me to start answering these, Dean.
Go ahead.
All right. It says, can you say about composite analysis in Nastran in CAD? What are the limitations? Which results, features can I interpolate, or things which are important? So this is from Carol. Carol, this is a really good question. So Nastran in CAD, it doesn't have Autodesk Simulation Composite Analysis built into it, this product that we're talking about. Okay. But Nastran in CAD does offer composite simulation capabilities, and Nastran in CAD is really meant for linear elastic responses of composite materials. And what it's very powerful for is understanding failure indices or strength ratios under a linear elastic sense. So you can determine when your first matrix failure will be or when your first fiber failure will be. And it offers you access to a lot of different failure theories for that. So our failure theory, multi-continuum theory is offered, Saiwu, Saihill, match stress I think is offered in there as well. But the main difference is that Nastran in CAD should be used to predict initial failure, and Autodesk Simulation Composite Analysis should be used to go past initial failure to ultimate failure of the structure. And there's different benefits to each one of those. Does that answer your question, Carol? I hope so. Eric has asked, any news, partially. Feel free to type what I did not answer in there, Carol. Eric has asked, any news for AME with ANSYS, also AME for unfilled plastics? So this is a great question, and Eric, I know you, so I'm glad that you brought this up. Currently, we are working on an integration with ANSYS with Advanced Material Exchange. So instead of only supporting Atticus, we would also support ANSYS, which would allow us to map data from mold flow to an ANSYS structural simulation. And we're also working on performing that for unfilled plastics, both in the linear and the nonlinear sense. And what that means is that you can run a simulation on mold flow, you can map over residual stress and strain fields as well as material properties for an unfilled plastic, and we will take those properties into a structural analysis. So for unfilled plastics, we won't require you to have nonlinear material data, but we would ask that you do have it if you want to do a nonlinear analysis. Hopefully that answers your question, Eric. You got it, Eric. Okay, Carol, let's keep going on this. Carol asks, could you be a little more specific about this analysis type? Only linear in Nastran in CAD regarding to composites. Yes. So Nastran in CAD is great for nonlinear simulation in regards to nonlinear material responses, and it's also very good for linear responses. But for composite materials, there needs to be, specifically for nonlinear simulation of composite materials, the meshing strategies need to be a little bit different, as well as how we degrade material properties needs to be a little bit different. So if you want to go past first ply failure, Carol, if you want to simulate what happens after you get your first matrix crack, I would suggest moving towards a finite element code like Abacus ANSYS or MSC, or even better, Autodesk Nastran, and then we can use Autodesk Simulation Composite Analysis coupled with that to take it past that first failure initiation. So basically, yes, only linear in Nastran in CAD. Regarding the composites, I think that's exactly right. Any other questions? No problem, Carol. All right. I think that's it, Dean.
Yeah, sounds good. I want to thank everybody for all the great questions and staying along with us. And if we'll be sending this video out after, so feel free to review it. And if you have any questions down the road, you can contact us. I don't have anything else, so we can probably go ahead and say goodbye for today, and then stay tuned for next month. We'll be giving another support webinar for composites. And feel free to tune into any of the other products that are available in this Simulation IQ series. So, all right.
Thanks, guys.
Thank you for coming.